going to do the last problem on our section about momentum and expectation values. And to be honest, I think that I might be misunderstanding this question a little bit, and maybe I'm making it a little bit easier than it needs to be. So in all fairness, I kind of had a little bit of issue like actually understanding, and I might be making it more trivial than it is because this is incredibly trivial. So this is going to be a really short video. So first it says, show that the wave function picks up a time-dependent phase factor of e to the I v naught t over h bar. If I had, instead of just v, I had v plus v naught. So we have our Schrodinger equation looking like this, and then I h bar to m del squared psi del x squared, and then minus I h bar v psi. Just go ahead and check that because I don't have a good memory, so I don't have any sense of pride about checking these things over and over again. So there we go. There's our form of our Schrodinger equation. Now, if I replace this v with v plus v naught, I can just shove it in there. And now instead of v, I'm gonna have v plus v naught, and it's real, it's not imaginary. That's going to be kind of key for the second part. And now we know that this form lends itself to, you know, some sort of time independent section of our wave function, and then plus this phase factor that is dependent on time. So, you know, we get something like we had in one of the earlier problems, e to the negative lambda x, and then our phase factor for our time. Now, here, just solving that out, our potential being just omega h bar means that our generalized form, I could write it as e to the negative I omega t, or I could, IV, like that, so we have a complex form, or I could write it as, you know, just solving it out, we have some exponential form where to get that phase factor in particular, we have something like this. So our solution is just e to the negative I v h bar t is our solution to that. And then we choose to rewrite that. I guess I don't need the I there. And then we choose to rewrite that as e to the I omega t, so that we have just our simple form of energy. Our potential energy is in the form of the frequency times h bar. If we have v plus v naught, then our phase factor becomes e to the I v plus v naught t over h bar, meaning that our solution is going to take this form, or I could write that this way: e to the negative iv over h bar t, and then e to the negative iv naught over h bar t, and there's where we get our extra phase factor. To be honest, I could be misinterpreting the question, because that seems to just be way too trivial. Okay, then we want to know, what does it have to do in the expectation value of a dynamic variable? I'm going to go ahead and take a variable such as expectation value of x being dx dx times the probability density, and we're just going to take the time derivative of that. So then I just get x d dt in there. And then I get d dt of psi complex conjugate psi. We're going to come down to this line because I am going to need the room. Okay, then using our product rule, so we have psi complex conjugate d psi dt plus d psi complex conjugate dt psi. So then replacing it with our Schrodinger equations up there, I get, so for our first one, I have negative I h bar 2m psi complex conjugate all of this minus I h bar psi complex conjugate v psi minus this with just v naught psi, and then I have plus. I'm going to do it down here. Now we have d complex conjugate of psi, which is going to give me negative signs d squared complex conjugate d psi squared, and then times psi, and then this one would be a plus. Oh, so that one just ends up being, I believe, just plus, and then we get plus here. Oh, this one was plus, this one's negative. There we go. And then this one ends up being a positive I h bar psi v psi complex conjugate plus I h bar psi v naught complex conjugate. So just like when we did this in the earlier section, these cancel, but since these are both real parts, just like the constant potential v, they also cancel as well. So then you could go on with the result to get the expectation value for the velocity, or the velocity of the expectation value of x. But I won't go that far, because basically at this part I know my answer. What effect does it have on the expectation value of a dynamical variable? It has no effect. Now fully admit I might, and very possibly and completely misunderstanding what this question's asking for, and in turn made it way too easy. But at any rate, that's the way that I read the question. And that's our last problem in Griffiths for momentum. And next time we're going to be looking at uncertainty values.